Please consider a question on a large scale. What is the overall shape of the universe? You may have never thought this was a problem. In many videos and pictures, I've seen depictions of the universe, which is often shown as a big black sphere expanding from that tiny point of the Big Bang. Well, first, let me tell you the answer directly. No, the universe is not a three-dimensional sphere. Please erase that shape from your mind first. Those videos are just for illustrative purposes. Next, please think carefully. What shape could the universe possibly be? Our Earth is roughly spherical, but the solar system is not a sphere. It's a very flat disk. The Milky Way is also a disk, but it has many spiral arms. Not all galaxies are disk-shaped. For example, the spiral galaxy IC 2163 is shaped like a pair of large eyes. DSO 13701 galaxy in Triangulum Australe looks like a giant jellyfish. So it can be said that shapes are incredibly diverse. Thus, the universe could also be any shape. If you are an ambitious cosmologist, you certainly wouldn't want to guess blindly. But we can't fly outside the universe to take a picture of it, so you can only hope to find some theories to help you narrow down the infinite possibilities to a few, preferably just one option. Right, there is one theory that can help us reduce the possibilities for the universe's shape from infinitely many to just three, and we are nearly close to finding the final answer. Not only that, this theory also determines the life and death pace of the universe, that is, whether time itself holds. Today, I want to talk to you about this concept, which may sound familiar at first, but is rarely broken down and explained in detail in the scientific field. Its name is symmetry. Have you ever wondered that the earth beneath our feet, the stars above our heads, and even the vast universe itself, the underlying code of their operation is hidden into seemingly simple sentences? Let's start with these two sentences. The great physicist Richard Feynman once said that if he had to summarize the most important discovery of modern science in one sentence, he would choose this: the world is made of atoms. This is because much of our understanding of the universe is based on theories about the properties of atoms and their interactions. Many prominent modern scientists believe that if they could choose one more sentence, it would be, "Symmetry is the foundation of the laws of the universe." Later, there emerged a joke in the scientific community. If human civilization were to perish, and we could only leave the sentences for future generations, these two should be, "The world is made of atoms," and "Symmetry is the foundation of the laws of the universe." Leaving these two sentences for posterity would save the next rising civilization hundreds of years of exploration. Over the past few centuries, countless revolutions have occurred in science. The most dynamic discoveries among them share a common point they all focus on: the properties that remain unchanged under many different operations in nature. This invariance is what physicists call symmetry, of course. The left-right symmetry we talk about in daily life is also included in this concept of symmetry. However, the symmetry physicists refer to is much broader. In many significant scientific advancements, symmetry has played a key role. So let's start with the geometric symmetry you're most familiar with. Pick up any white billiard ball from the table and hold it in your hand, rotate it. Or take a plain, patternless round plate and rotate it around its center. They appear unchanged during rotation. You can also pick up a freshly fallen snowflake. Rotate each of its corners to the position of the adjacent corner. This can't be done arbitrarily. You can only rotate by a fixed angle, and you'll find it hard till the snowflake has been rotated. Or you can take the letter and flip it along its vertical axis. You'll get a letter that looks exactly the same. The symmetry an object possesses refers to such an operation, whether real or imagined. As long as under this operation, the object appears unchanged, we can call this operation a symmetry of the object. For an object, the more types of operations that keep it unchanged, the more symmetry it possesses. A perfect sphere like a white billiard ball has a high degree of symmetry because any rotation that passes through the center of the sphere cannot make the sphere look any different. A cube, however, has less symmetry because only rotations around the central axis perpendicular to its surfaces by 90 degrees can keep the cube unchanged. If someone rotates the cube in another way, say by 45 degrees, you can still recognize it as the original cube, but you'll also notice it has been rotated. As for the letter we mentioned earlier, its degrees of freedom are even fewer. You can only flip it left-right along its vertical central axis, or rotate it by 180 degrees, for it to appear unchanged. However, in physics, the scope of symmetry is much broader. The operations we can perform on an object are not limited to rotations or flips. We can think about this in a more abstract way. Regardless of what operation is applied to you or the environment, whether this operation occurs in reality or is imagined, this operation should keep the laws that explain the physical phenomena you observe unchanged. Let me emphasize, it is an operation that keeps the laws of physical phenomena unchanged. It's important to note that the symmetry operation here does not require your observed results to remain the same. What we truly care about is whether the laws behind these observations remain unchanged under the symmetry operation. To explain in more detail are the laws used to explain your observations before the symmetry operation, exactly the same as the laws used to explain your observations after the symmetry operation. Let's use an example to illustrate. Suppose you are a gymnast who has been training for the Olympics for several years. You can easily complete every set of moves in your gymnastics routine. You know exactly how much force to use on the balance beam to perform a front tuck, how high to jump on the floor to complete a straight back somersault with a 720-degree twist, and how fast to swing your body on the parallel bars to execute a perfect backflip. It seems your body has an instinctive feel for Newton's laws now. The Olympic competition is about to begin. You'll fly to the United States to perform in front of a live audience. You certainly hope Newton's laws remain unchanged. Newton's laws can indeed meet this expectation. They do not change with location. Even if you move to a different place, the laws governing your body won't be affected at all. This is like the billiard ball appearing unchanged when rotated. This kind of symmetry is called translational symmetry in physics, or translational invariance. Translational symmetry holds not only in Newton's laws, but also in Maxwell's laws describing electromagnetic interactions, Einstein's special relativity, even general relativity, quantum mechanics, and various theories in modern physics. We must emphasize again, it is the physical laws that remain unchanged, not the observed results. Your observations and experiences will differ due to changes in your location. For example, if you perform gymnastics on the moon, you'll find that when you jump with the same leg strength, the trajectory of your bounce is completely different from that on Earth. But we understand the difference, knowing it is caused by physical laws. Because the moon is much lighter than Earth, the gravitational force it can generate is much smaller, resulting in a completely different upward trajectory compared to Earth. And this law, that the strength of gravity depends on mass, is part of Newton's law of gravitation. The differences you feel on Earth and the moon do not indicate that the law of gravitation changes with time or location. But consider this, physical laws don't necessarily have to be this way. We can imagine a new universe where physical laws change with time and location. The physical laws we know on Earth would be completely useless for understanding the moon, the Andromeda Galaxy, the Crab Nebula, or the physical laws at any other location in the universe. In fact, even in our own universe, we aren't entirely certain whether the physical laws that work on Earth are also valid in distant places. But we do know that if physical laws somewhere in the universe differ from what we think, they must find an exit somewhere to reconcile this difference. Otherwise, it would be impossible to explain the phenomena we observe. Increasingly precise astronomical observations have provided us with sufficiently credible evidence that physical laws remain consistent throughout cosmic space, or more accurately, at least, in the observable universe we can currently see. This point further highlights the magical power of symmetry. Although we are confined to Earth and its vicinity, the existence of spatial translational invariance allows us to understand the fundamental laws of the entire universe without leaving our planet, because the physical laws discovered here are also the laws of the entire universe. Rotational symmetry or rotational invariance, along with translational invariance, are actually close relatives. These symmetries are based on the idea that different spatial directions have equal status. You might find it strange on Earth you feel that up and down are different. Note that this is a difference in environment, not a difference in physical laws. If you leave Earth and float in outer space, far away from any galaxy or other celestial body, symmetry becomes apparent in the dark void of space. You cannot find a special direction, up, down, and all around are the same. If you plan to build a laboratory to explore the nature of matter or forces, you don't need to worry about its orientation, because the fundamental laws are not affected by the laboratory's orientation. Besides this spatial directional symmetry, physics also follows another type of symmetry. If your outer space laboratory moves at a constant velocity, whether at 5 kilometers per hour or 100,000 kilometers per hour, these motions will not have any effect on the physical laws. Use to explain your experimental observations. Einstein took this a step further. He proposed the symmetry of light, elevating the speed of light to the status of an inviolable law of nature and declaring it unaffected by motion, just as a white billiard ball does not change when rotated. The speed of light remains constant. We have discussed this in detail in a previous episode. Those who haven't heard it can go listen. Einstein's next major scientific contribution, general relativity, advanced in this direction, moving toward theories with greater symmetry. You can think of special relativity as establishing symmetry between observers moving at constant velocities relative to each other. You can also think of general relativity as an advanced version of special relativity, establishing symmetry between points, accelerating relative to each other. In the universe, you cannot feel constant velocity motion, but you can feel accelerated motion. The physics laws describing your observations should appear different due to your acceleration to explain the extra force you feel. This is exactly the case in Newtonian theory, but Einstein realized that you cannot distinguish between acceleration and a gravitational field. Once we add a suitable gravitational field to the external physical conditions, the physical laws do not change when you accelerate. In the framework of general relativity, all observers, even those undergoing accelerated motion, have equal status. They are completely symmetric with each other because each observer can claim to be at rest as long as they attribute the forces they feel to different gravitational field effects. This is similar to the differences you feel when doing gymnastics on Earth versus the Moon over the past few decades. Physicists have elevated the principle of symmetry to the highest rung of our scientific exploration ladder. Whenever someone proposes a new law of nature, they naturally ask, why should this law exist? Why should special relativity exist? Why should general relativity exist? Why should Maxwell's electromagnetic theory exist? Why should Young-Mills field theory for strong and weak interactions exist? It can be said that physicists feel these theories might be correct, and the idea of symmetry is the most crucial reason for this feeling, precisely because there is no reason to believe that there exists a unique location in the universe. Compared to other locations, physicists have confidence that translational symmetry is widespread in natural laws, precisely because there is no reason to believe that there exists a unique constant motion in the universe. Compared to other constant motions, physicists have sufficient confidence in special relativity, and precisely because there is no reason to believe that any observation point, whether accelerating or not, is different from other observation points. Physicists have sufficient confidence in general relativity. It can be said that, for scientists, symmetry is not a consequence of natural laws, but the foundation of natural laws. Without symmetry, the entire edifice of modern science would collapse. If one day you propose a new theory that challenges some symmetry, it will face the most rigorous scrutiny from the scientific community. But there is one thing you must have guessed. That is time, which we have discussed many times. Symmetry is also crucial for time. No one can give a clear, fundamental definition of time, but undoubtedly, Time is the recorder of cosmic change. Things in the universe gradually change, becoming different from before, making us aware of the passage of time. The hands of a watch point to different numbers. The sun's position in the sky changes. Carbon dioxide molecules escaping from a soda bottle disperse in all directions. All these indicate that things have changed, and the role of time is to help us notice these changes. According to John Wheeler, time is nature's clever way of ensuring that everything, all changes, do not happen all once. The existence of time depends on the absence of a special kind of symmetry. If there were perfect symmetry between today's world and the past world, if changes in time, like rotating a white billiard ball, brought no change at all, then the time we perceive would effectively not exist. We previously spent 3 episodes discussing the disappearance of time in classical physics and its return in modern physics today. We won't reopen that topic here. Instead, let's consider another question. Please think. Since relativity tells us that the rate at which time passes depends on your speed of motion and the strength of the gravitational field you are in. This point is clear to regular listeners of our show. That is, if you keep accelerating until you approach the speed of light, your time flow will slow down more and more. So we can't help but ask, when astronomers and physicists talk about the age of the entire universe, that the universe began about 14 billion years ago. Relative to whom is this 14 billion years? Which clock gives this 14 billion years? If there is a galaxy very far away from us, moving at a very high speed relative to us, would intelligent life in that galaxy also conclude that the universe is 14 billion years old? If so, what ensures that their clocks are synchronized with ours? The answers to these questions also depend on symmetry, specifically symmetry in space. Over 40 years ago, scientists discovered that the universe is filled with cosmic microwave background radiation. It is the remnant of the extremely hot environment just after the Big Bang cooled down to today. The early universe was in an unimaginably hot state, but as the universe evolved and expanded, the radiation was steadily and continuously diluted, slowly cooling today. The temperature of the microwave radiation is only to 0.7 Kelvin above absolute zero. Cosmic microwave background radiation is to astronomers what dinosaur bones are to paleontologists. Through satellite observations over the past decade, we have discovered an important characteristic of this radiation. Its distribution is extremely uniform. The differences in microwave background radiation across different regions of the sky are less than 1 part in 1,000 on Earth. Such tiny differences would render weather forecasts meaningless. It would be as if the weather were exactly the same everywhere on Earth. But on a cosmic scale, this uniformity in radiation temperature is very important for 2 reasons. First, the uniformity of radiation temperature provides observational evidence that the early universe was not dominated by huge, high-entropy clumps of matter, such as black holes, because such an uneven material environment would leave similarly uneven radiation traces. Instead, the uniformity of radiation temperature proves that the young universe was isotropic. Isotropy implies low entropy, which is good. because our discussion on the arrow of time requires the universe to start with low entropy second. Although the universe originated from the Big Bang, overall, the evolution across the universe should be similar, since the temperature here is the same as elsewhere in the universe. The physical conditions in every part of the universe must have evolved in the same way since the Big Bang. This inference is very important, but we need to understand it correctly. When we look up at the sky at first glance, it doesn't seem uniform. Various planets and stars twinkle within. The key here is that when analyzing the entire universe, we adopt a macro perspective. These small-scale differences, and small here should be in quotes, their differences can be completely averaged out. On a large scale, the universe is uniform. This is like a glass of water. At the molecular level, water is chaotic. Here's an HO molecule, there's nothing. And over there are two HO molecules, but if we average over small-scale water molecules, considering only the large-scale water visible to the naked eye in daily life, we find that water is clear and uniform. This conclusion is very important because it allows us to define a concept of time for the entire universe. If we consider the degree of change as an effective definition of the passage of time, and the uniformity of physical conditions across space proves the uniformity of cosmic change, then we can know that the passage of time is also uniform. For example, this is like the uniformity of Earth's geological structure. Here, uniform is also on a large scale. After averaging, this uniformity allows geologists from the Americas, Asia, and Africa to agree on Earth's history and age without geologists from the Americas and Asia arriving at different Earth ages due to uneven geological conditions. It is the same. The uniformity of cosmic evolution also allows physicists living in different galaxies to reach a consensus on the history and age of the universe. But be careful, here we encounter a core problem again. If the universe possessed perfect symmetry, meaning it was in a completely unchanging state, then even defining time would become very difficult. On the other hand, if the universe had no symmetry in space at all, for example, if the background radiation were completely chaotic with huge temperature differences across regions, then the concept of time in cosmology would also become meaningless. Clocks in different places would run at different speeds. If you wanted to know what the universe was like at 3 billion years old, the answer would depend on which clock you use. To measure the passage of those 3 billion years, that would be extremely complicated. So you see, very fortunately, our universe is neither so symmetric that time loses all meaning, nor completely devoid of symmetry. This allows us to avoid that completely incalculable complexity, enabling us to discuss the total age of the universe and its evolution over time. We often ask, why can humans observe and understand the universe? I think this is a gift the universe has given us. There is symmetry in many places, but not complete symmetry now. Let's focus again on the evolution of the universe. To put it simply, the history of the universe is this: the universe is expanding. In 1929, Edwin Hubble discovered that the dozens of galaxies he observed through his telescope were all moving away from him and the farther a galaxy was, the faster it moved away. A galaxy 100 million light-years away moves away from us at 5.5 million kilometers per hour. A galaxy 200 million light-years away moves twice as fast at 11 million kilometers per hour, and a galaxy 300 million light-years away moves 3 times as fast, and so on. The later story, Based on this phenomenon, people deduced that the universe must have begun with a Big Bang. But there is also a problem here. If the universe were like a bomb exploding, with all galaxies flying apart like bomb fragments, then some fragments would fly in opposite directions, and some would fly in the same direction. And if Earth were on a random fragment, we should observe that some galaxies are stationary relative to us, because some fragments would be flying in the same direction as us. But that's not the case. We see that all galaxies are moving away from us. So a reasonable inference is that we happen to be exactly at the center of the Big Bang, because only then would we see galaxies in all directions moving away from us at consistent speeds, provided they are at similar distances, rather than galaxies in the east moving away faster and galaxies in the west moving away slower. If it were really like that, this theory would have to bear a deep-seated asymmetry. Regions far from the explosion center, those far away from us, would be very different from our location, but astronomical experimental data do not provide evidence for such a symmetry. As we've said many times before, all places in the universe appear to be similar. At the same time, we highly doubt that it's just a coincidence that we were born exactly at the center of the universe. This requires a more complex explanation for Hubble's discovery. In this new explanation, our location should not hold any special status in the universe, otherwise it would conflict with the symmetry we uphold. General relativity eventually provided such an explanation. Einstein discovered that space and time are variable, not fixed. They are elastic, not rigid. His equations accurately tell us how space and time change with the presence of matter and energy. Later, in the 1920s, the Russian mathematician Alexander Friedman analyzed Einstein's equations and obtained surprising results. He realized that gravity permeating all of space would cause the structure of space itself to change. Under this new explanation, matter in the universe does not fly apart like bomb fragments in a fixed space. Rather, space itself is expanding. The expansion of space pulls the galaxies within it apart. These galaxies, in fact, have no motion relative to space itself. Here's a more understandable example. It's like drawing many dots on a balloon. When the balloon is inflated, each dot moves away from the others, and from any dot, you see all other dots moving away from you. But there is no special point on the balloon that is the center of the explosion. The expansion of the universe is similar from any position. Looking at yourself, it seems as if you are at the center of the explosion. Observers in any galaxy, like us, see all other galaxies moving away from them, and the farther away the dot, the faster it moves away. This recession effect can also be calculated using the balloon example again. If the balloon doubles in size over some time, all spatial distances become twice as large. Then, dots originally 1 meter apart are now 2 meters apart. Dots originally 5 meters apart become 10 meters apart. Dots originally 1 kilometer apart are now 2 kilometers apart. That is, over a certain period, the increase in distance between two dots is proportional to their initial separation. The farther apart two dots are, the more space between them, and when space expands, the increase in their distance is more significant. You might say, the center point inside the balloon is a special point because all points on the balloon surface are moving away from it. So we must emphasize in this analogy, the only valid part is the two-dimensional surface of the balloon. We use this two-dimensional surface to help you understand the three-dimensional space of the universe. This will be very important later in describing the shape of the universe. This balloon analogy also helps you understand why the entire universe is expanding, but we don't see this expansion happening around us, like your table moving away from you or Jupiter moving away from us, because on the large scale of the universe, the distances between these objects are so small that the expansion of such small spaces is negligible in measurement. It's like having two dots on the balloon that are almost touching, even if the balloon is inflated greatly. Compared to dots originally far apart, these two closely placed dots remain close together. Next, let's imagine a variant of the balloon, deriving a concept of time applicable to the entire universe. From spatial symmetry, you can replace each dot on the balloon with a clock when the balloon starts to inflate. These clocks start timing separately since all clocks move away from each other as space expands, and their relative recession speeds, -1, depending on their pairwise separations with such motion, as suggested by Einstein's special relativity, cause these clocks to lose synchronization. For real clocks on a balloon surface, yes, they would. But when extending this balloon concept to the expansion of the entire universe, they wouldn't. The difference here is that relativity states that clocks traveling through space along different paths and speeds will have different ticking rates. But if the balloon represents space itself, and each small clock is attached to a fixed point on the balloon surface relative to the balloon, it is not traveling through space. Therefore, they can operate at exactly the same rate. This is why we say that in the Big Bang Theory, the recession speed of distant galaxies can exceed the speed of light because they are not moving through space at light speed. Rather, the effect of space itself expanding makes them appear to recede faster than light. This does not violate relativity, of course. If you carry a watch and travel through space at near light speed, your clock will slow down, and the universe's age you observe will change accordingly. But remember, when astronomers discuss the age of the universe, they refer to the total time average over the entire universe. The uniformity of the cosmic microwave background radiation we mentioned earlier can itself be used to test whether we are moving through space at high speed. Once you are in high-speed motion relative to space, you would no longer observe this symmetry or invariance. It's like the siren of a police car speeding toward us sounds sharper, and when moving rapidly away, the siren sounds deeper. The cosmic microwave background radiation behaves similarly. If you pilot a high-speed spacecraft through space, then the peaks and troughs of microwaves coming toward you would oscillate at a higher frequency, while those catching up from behind would oscillate at a lower frequency. Higher frequency microwaves mean higher radiation temperature, so you would feel the radiation temperature in front of you is higher than behind you. Actual measurements show that. On our spaceship Earth, astronomers have indeed found that the cosmic microwave background radiation in one direction is slightly hotter and in the opposite direction slightly cooler. This fact tells us precisely that not only is Earth orbiting the Sun and the Sun orbiting the galactic center, but the entire Milky Way is moving at a small speed, exceeding the universe's expansion rate toward the direction of the Hydra constellation. Actually, knowing this fact solved a long-standing puzzle in my mind. When we say galaxies are moving, relative to what are they moving? They should be moving relative to space, right? But we cannot measure where that so-called space is. It turns out we can detect our motion relative to space through tiny differences in the cosmic microwave background radiation in different directions. That's really quite fascinating. Earlier, we said something that needs re-emphasis. The entire Milky Way is moving at a speed toward the Hydra constellation, the speed that is a small velocity slightly exceeding the universe's expansion rate. What does this mean? Remember the balloon we talked about? The rate at which the balloon inflates is the universe's expansion rate, or the rate of space expansion. If our velocity relative to the universe's space itself were zero, that would mean our recession from other galaxies is entirely due to the expansion of space itself. Just like the balloon being inflated, and we are like dots welded onto the balloon surface. If we, as a dot, move relative to this balloon surface, that movement speed is what we just call the small velocity slightly exceeding the universe's expansion rate. Astronomers need to first adjust for the influence of this relatively small velocity on the cosmic microwave background radiation before they can clearly see the uniformity of the cosmic microwave background radiation. In other words, we need to subtract the front-back difference in microwave background radiation caused by our motion relative to space itself. After subtracting that, we observe the cosmic microwave background radiation in different directions. After this operation, we find that temperatures across the sky are actually very consistent. It is this uniformity and symmetry between positions that allows us to accurately discuss time when describing the entire universe. Now, let's answer the initial question. If someone asks you, what shape is the universe overall? How would you answer? You know, we live on a small planet that orbits an ordinary star, and our solar system is just one system at the edge of the Milky Way, no more special than the hundreds of millions of other galaxies. So, how can you have an understanding of the shape of the entire universe? At this point, symmetry can be used if you are willing to adopt the belief long held by scientists that on a large scale, all positions and all directions in the universe are symmetric relative to each other. Then you can answer this question. Most shapes cannot meet this symmetry criterion. They always have some region different from others. For example, A pear shape is narrow at the top and wide at the bottom. An egg shape is pointed at both ends and thick in the middle. These shapes have some symmetry, but not complete symmetry. You probably thought of a sphere again, right? The answer is no, because if the universe were a sphere, its center and edges would be different, as we said with the balloon analogy. The center point inside the balloon is the most special. And in using this analogy, I repeatedly emphasized that the focus is not the entire balloon, but the two-dimensional surface of the balloon. On that surface, no point is special compared to others. All points are symmetric. But the universe is obviously not a two-dimensional plane. So, according to the principle of symmetry, it should be a three-dimensional spherical surface. Note, not a three-dimensional sphere, but a three-dimensional spherical surface. This spherical surface is hard to visualize. Put simply, if a sphere is made of many, many points, starting from a random point inside and walking in one direction, you would eventually hit the wall of the sphere's surface, and then you couldn't go further but on a three-dimensional spherical surface, starting from any point and walking continuously in one direction. You would eventually return to the starting point. This is similar to starting from any point on Earth's two-dimensional spherical surface and eventually returning to the origin. So a three-dimensional spherical surface is one option, but not the only one. You can imagine an infinitely wide, infinitely long rubber sheet that is somewhat curved, but not completely curved. As this sheet extends, we still get complete symmetry. Extending this sheet's shape from 2D to 3D, you get an infinitely extended but uncurved universe. Unlike the universe curved into a three-dimensional spherical surface, scientists call this a flat universe. In this universe, you would never reach an edge, but you would also never return to the starting point, since there is no edge. There's no way to describe what shape it is. Both the infinite flat universe and the three-dimensional spherical surface help us avoid a problem. What is outside the boundary of space? What happens if you reach the boundary of space? If space has no boundary, these questions are meaningless. The difference between the two is that the spherical surface's three-dimensional boundary is completely closed, while the infinitely extending flat universe's boundary is not curled up on itself, but extends outward infinitely. There is another possible shape for a symmetric universe. It is similar to the three-dimensional spherical surface. You cannot draw it, or even easily imagine it, but we can use its two-dimensional version for explanation. In the two-dimensional simplified version of this cosmic shape, you can imagine a potato chip. This chip is also infinitely large. From one direction, it curves downward, and from another direction, it curves upward. It is generally called a saddle surface. It is an anti-sphere. The spherical surface is highly symmetric and bulges outward, while the saddle surface is highly symmetric and caves inward. Note, the bulging and caving here refer to the two-dimensional simplified version more rigorously in mathematics. We say the spherical surface has positive curvature. Bulging outward, the saddle surface has negative curvature. Caving inward, flat space has zero curvature. Congratulations, you now know all the conjectures about the shape of the universe in the physics community. These aren't casual guesses by laypeople. But the current mainstream scientific opinion, physicists have proven that under the requirement of symmetry, that is, when we require all positions and directions to have no specialness, the three possibilities are exhausted by the positively curved three-dimensional spherical surface, the negatively curved three-dimensional saddle surface, and the zero curvature three-dimensional flat space. The shape of the universe can only be one of these three. Thinking carefully, it's truly amazing. The shape of the entire universe could have had infinite possibilities. But with the powerful tool of symmetry, scientists have eliminated most possibilities. However, symmetry can only take us this far. Which of these three is the true shape of the universe? We need to turn to general relativity, Einstein's equations. Take all matter and energy in the universe as input. Through calculation, we can obtain the spatial curvature, positive, negative, or zero. The difficulty here is that, for decades, astronomers have been unable to definitively determine this input value, how much matter and energy the universe actually contains. The sum of all matter and energy divided by the total volume of space gives us a critical number called the critical density. If all matter and energy in the universe are uniformly distributed throughout space, and their density is greater than the so-called critical density, the spatial curvature obtained from Einstein's equations will be positive. If less than this critical density, spatial curvature will be negative. If exactly equal to this number, spatial curvature 0. The best current data suggests that spatial curvature 0. That is, among those three shapes, the universe is more likely to be flat. What does this correspond to in terms of matter density? It is about 0.000 with 23 zeros, or 10 to 23 grams per cubic meter. In other words, there are only about 5 hydrogen atoms per cubic meter. This number represents extreme emptiness. You can imagine that on Earth, the Moon, Jupiter, anywhere you can think of, the density is far greater than this number. But remember, this number is averaged over much larger emptiness. Between galaxies lie unimaginably vast cosmic spaces where there is truly nothing but stranger, and this critical density's emptiness is why the universe's curvature so close to 0. It could have been any positive or negative value, but it is almost exactly 0. It's hard to believe this is just a coincidence. If you think a coincidence is just a coincidence, then your curiosity is not enough to make you a physicist. On the path to exploring this question, physicists have discovered many remarkable things. That is another vast topic, which we'll expand on another day. Finally, let's summarize. If we guessed randomly, the shape of the universe could be any form. It is the principle of symmetry that has brought us to these specific few options. Thinking about symmetry has become an indispensable part of modern cosmology. It gives meaning to the overall time of the universe, determines the overall shape of the universe, and even influences the theoretical framework of general relativity. Everything we know relies on symmetry. When we move from the vast universe to the microscopic quantum world, we still cannot escape the control of symmetry. Symmetry is like a mysterious golden thread connecting microscopic atoms and the vast universe. It gives physical laws universality, making the physical laws on Earth highly consistent with those anywhere in the universe. It brings our entire universe from disorder to order. Every inquiry into symmetry expands the boundaries of human knowledge and brings us one step closer to the ultimate secrets of the universe.